Alrighty, folks. Today, volcanoes. Wow, that's quite bright in the dim room. Pretty picture, isn't it? Yeah. This is a great segue, gateway, I don't know what the word would be, to talk about scientists in the media. It's pretty. It's awesome. It's amazing. Makes a hell of a picture. But it's also potentially wiping out a neighborhood or a forest or this, that, or the other thing. The hurricane. We talked about those a little while, showed you some pictures from above. I commented on how amazing and beautiful and artworky it was. And it killed all those people and ruined, countless lives. And these scientists, I won't say these poor scientists. Scientists usually are poor, but not in this sense. They get interviewed on TV and they're so excited. And they sometimes come off as callous or disregard. No. Imagine if you were an accountant, all right? I know there's not a whole lot of science majors in here, so we'll talk about accounting just because it's the easiest thing to show an example. And let's just say you get this case that, oh my God, this person was just absolutely horrible and or evil and or whatever, embezzling for 15 years and 30 years. And you're just like, oh my God, I can't wait to get into this. This is going to be so awesome. I love accounting and. Okay? It's the same idea. These people have spent a good chunk of their lives studying this stuff. And they can't help sometimes but show enthusiasm and or even smile during said catastrophes. You're not going to hire PR people or anything like that for scientists, but it just, I think sometimes, and we saw in the St. Helens video, some of the same things going on there. It's what they do, and it's not necessarily a once-in-a-lifetime event, but boy, it sure doesn't happen very often. So, and I make similar comments too, just, how beautiful this is or how beautiful that is. And, well, it is unless you're, half a mile away. So, that's still pretty freaking awesome though, isn't it? I honestly don't know, especially in this day and age where you cite everything. I'm really surprised I didn't cite this image. So I assume this is a real picture, as amazing of a picture as it would be, and it's not a graphic or a cartoon. I just added it too, like a semester or two ago. But better than the plain red and black that this PowerPoint had been for years. I still kept with the red and black, obviously, but. So, three things that come out of a volcano. That's kind of really generic, sort of a Family Feud kind of question. But it does set up a good deal of conversation for us. All right. The obvious thing there is lava. And you guys are far enough along now. It depends on the semester. Sometimes I do volcanoes first. Sometimes I do igneous rocks first. It varies. Earth science, they don't even really get a solid conversation about igneous rocks. It just gets introduced during the rock cycle. But at any rate, this semester, we've had it, so you know that lava comes in at least three flavors, right? You got your felsic, your mafic, and your blend, the intermediate, just like igneous rocks. All of your fine-grained igneous rocks were lavas. And we'll get into that and a little more. Pyroclastics. What do you guys think that is? Word's kind of cut off there on the screen. I apologize. What does pyro mean? Fire, yeah. Okay. You might call one of your buddies a pyro or something if they're always playing with a lighter or matches. But yeah, it comes from fire there. Clasts is a word you'll see again when we do sedimentary rocks. Clasts are rock fragments. So pyroclastic material is simply put fire rock. Okay. Well, fire rock comes in a handful of sizes. You're familiar with one of them already. It's called ash. All right, and again, we'll talk about that for a couple slides. Last but not least, we've got gases. And I'm sure you're aware, again, that this isn't exactly, wonderful stuff to breathe in that comes out of a volcano. It's coffee and choking and all that horrible stuff. And you may even be aware that sometimes, just a leak out of one of these things, a sort of volcanic fart, we'll call it a little later, can wipe out a whole village with just the gas, not even having to lava or ash. All right. But what a lot of folks don't know is that the most amount of gas that comes out of here is in the form of water vapor. All right, good old H2O. All of that thick, black, billowing smoke that we see coming out of these volcanoes is really just dirty water vapor, the ash and whatnot mixed in with it. And as I said, we'll talk about that for a little bit. There, see, that's what this PowerPoint used to look like. Thematic, but, So this slide has a lot of information on it, and it's rather fine fonted. I apologize for that, but I don't really, as always, want you just to copy down the slide anyhow. We're a little more interested in the pictures on the left-hand side, and I'm sure you can see those. And what we really are using this diagram for then are the three types of volcanoes. Okay, the three types of volcanoes, or the three ways that they can look, the three shapes if you want to. And they are simply put, and then we'll go back through and talk about them. You have the shield cone. The cone is what we call the volcano or the mountain itself. Okay, so shield, like a Roman shield or a Viking shield kind of thing. Cinder cone. Cinder with a C. And a composite cone. So shield, cinder, and composite. Now what this slide really doesn't do is give you an idea of scale. There's a scale bar in there, but only if you stop to look at it and so on and so forth and then remember and have a context for how big those numbers are, then maybe it's kind of useful. The shield cones are arguably the largest. Okay, not just in width, but in height. If you're looking at it, you're like, that doesn't look. I know, that's exactly my point. Okay, it's not a great job of putting stuff to scale. What makes that different? See that blue? That's the ocean. So these are those islands. Okay, and I know you never really thought about, didn't think that the islands were just floating there. No, they go all the way down. But you got to process how far all the way down is. Okay. These things start on the ocean floor. They grow over thousands and thousands and thousands of years until they break through the water. If they continue to be active, they'll probably continue to grow a little bit. But that whole time, we haven't talked about weathering and erosion formally yet, but I'm sure you can guess that those waves are going to start beating on that thing and breaking it down and wearing it away and all that. So the shield cones are the biggest. I'm never going to ask you how tall they are, but they're the largest, the tallest. They're also, for lack of a better word, the most docile. We're going to show you some pictures a little later of some folks working around some volcanoes. And those are almost always going to be shield cones. Not always, but most often. They don't have a whole lot of embedded gas in them. In lab, we talked about our vesicular specimens. We mentioned it in the igneous rocks chapter as well. Those specimens that have holes in them, pores, pockets, whatever you want to say, like your pumice and your scoria. Okay, those come from a lava that had a lot of gas in it. As the gas bubbled out, right, it left those little pock marks here and there. Well, it's not to say that these kind of rocks don't have any gas, but not enough to make them these nasty, horrible, explosive things that we're going to talk about a couple minutes from now. This is more like a fountain at the mall, if you would, okay, or maybe a Disney volcano. It's going to bubble up and roll down the sides and float here, or not float, flow here and flow there. Still dangerous, right? If you're a rock, a tree, a house, something that can't move, out of the way. Still very troublesome. So still dangerous, but not in a, bury a village at 5:30 in the morning while everyone's still asleep kind of way, okay? Now, because these aren't horribly sputtery and spitty and nasty, as I said, the lava just sort of flows out, well, that lends itself to its shape. You got to remember these things start with a hole in the earth, a crack in the crust, right? And the lava just sort of bubbles out, flows to the side. And again, just picture some, 70s hippy-dippy candle sitting in the middle of a table, just some big flowy thing. And that's what these are, except they're monstrous. They're huge. So very gentle slopes, very wide base. That's some of the stuff that's mentioned there in code there. It talks about degrees of incline. Again, let's use the word gentle instead of 10 degrees, okay? The last thing I want to tell you is, actually two things, but the next thing I want to tell you is that these are primarily basaltic. All right, you remember basalt, and in geology class you remember that when I say the word basalt, I'm never going to hold a hunk up in here, but when I say basalt, hopefully you picture that fine-grained black rock, okay? And maybe you're aware that Hawaii is known for its black sand beaches. That's why. All right. Hawaiian Islands are a great example of shield volcanoes. And when that rock breaks down, because of the waves and so on and so forth, all right, well, rock breaks into pieces, parts, eventually sand-sized grains. Yeah, question?
How do you see that name of the Hawaiian volcano,
Mauna Loa is that one. Yeah, there's several. And I will be the first to tell you I do not know my Hawaiian Islands in order, and this, that, and the other. I could ramble off some random Hawaiian names, but strangely, I know the name of the next island. They say it won't be up for a couple thousand years. It's Loihi. All right, it's still way down low underneath the ocean, but it is building up. We'll talk a good bit about these informally, actually, because they're great evidence, as it turns out, for plate tectonics. All right, there's a string of islands, and only one or one and a half or two are active. And what they found out actually is that they also get older as they go off to the northwest, I think it is. So what happens is we've got this plate moving over the spot where the magma is, and over time it just sort of shifts off and it starts working on a new island. So pretty cool stuff. So you need to know shield volcanoes are wide base, low angle, start on the ocean floor. They're the biggest, not necessarily the baddest. And basalt and Hawaiian Islands. What is that, like 6 things? Awesome. Now let's jump to the totally other end of the spectrum, cinder cones. Less than 300 meters. Very few of you think in metric, I know that. Some of you do. How many feet to a meter? 3. All right. Less than 900 feet. Now, yeah, 900 feet, that's pretty high, but not compared to 10,000 kilometers, which was the other guy. Okay, these are little volcanoes, by comparison. It's 5,000 feet to a mile, right? So we're talking about less than 900 feet. So less than a fifth of a mile. Hell, I could probably even jog that. Okay? Not uphill, mind you, but straight. At any rate, significantly different. And they are this way because of their nature. Where the other guys were very flowy lava. Oh, for those of you that don't know it at home, I'm fat, so that was a fat joke. So while the other guy was big flowy lava, these things are like those sputtery cones you might have had on the 4th of July. Okay, they're shooting out stuff like popcorn going off left and to the right. They're nasty, sputtery, evil things. These are the kind where you hear about a farmer comes back to the field the next day to find a volcano in the middle of it, kind of thing. All right, they grow up overnight, out of nowhere, and they can be gone just as fast, unfortunately blowing everything to smithereens along the way. So these things are chock full of gas, and because of that, like I said, we don't get those nice lava flows. We tend to see the pyroclastic material. All right, imagine that as like lava that's trying to flow out, but there's just this air pressure or gas pressure that just keeps sputtering it, like a spray paint can that's running out of paint, all right, or something along those lines. So, completely different things. These can be anywhere, okay? So I'm not going to give you a place to remember them, other than they can be anywhere. And I don't even want you to remember a rock type. We're going to have a rock type and a location for the next one, though. So cinder cones, they're small, they're very steep, all right? Nasty, sputtery things. So guess what a composite is? That's right, it's a mixture of both, okay? These are big, and these are the ones that you, short of Hawaiian Islands and Iceland and a handful of other places that are those volcanoes that grow from the ocean floor, these are the ones you know. This is Mount St. Helens. This is Mount Rainier. This is Mount Fuji, Kilimanjaro, Pele, all of those names that you know, that's these guys, okay? They start on land, and they go a couple thousand meters. And because they more or less alternate, it's not like they line up and take turns or anything, but because they more or less alternate, you're going to get those eruptions where it is lava flowing and it builds up that base, big and wide. And then you're going to get times when it blows itself to smithereens and maybe takes half the top off of it, like St. Helens did in the video, okay? Or it may just sit there and you grow up not even knowing it was a volcano. I had no idea Mount Rainier. Like when I was a kid, everyone was trying to climb Mount Rainier, right? It's Mount Everest, but it was in America. It was really tall and hard to do. I'm like, what? These people are trying to climb a volcano? That doesn't sound safe. Well, geologic time being what it is, it's safer than you would, safe as mountain climbing can be, at any rate. So the problem with these guys, and again, because for the most part volcanoes live in their own time frames, right? We've sort of built civilizations around these things. All the ones in Europe, other countries. Okay, I can speak mostly to the ones in America, of course. But these are what we have down the west coast of North America. These are our continental American volcanoes. The Hawaiian Islands, still America, but not continental. Denali, there's another one. All right, and you're thinking, oh yeah, these are all just big mountains. That's why. So we've built up these cities around them, or at least fairly close to them, and other countries have as well too, because you're going hundreds, 200, 300 years sometimes in between eruptions. It's enough for people to forget, and we don't know what type of eruption they're going to have when they do erupt. They're working on that, believe me. Testing chemistries, if it's an open kind of pit. very seldom do you see those, like Lord of the Rings, throw a ring or a virgin into it, kind of big cauldron-y pit-looking things. You don't see that very often, but they leak and so on and so forth. And so when they can test the lava, they try to and see, okay, well, if the chemistry is this, it turns out it can vary a little bit. Stuff we don't need to worry about, but I'm just trying to give you a little backstory here. They're working on predicting. But because we don't know how to do that yet, arguably, any time it starts to rumble, they need to be concerned. Kind of like earthquakes. They're still working on that too. These are mostly andesitic, andesite. Andesite was an intermediate rock. Okay, you had a hunk in lab. And again, your example, and you'll see this again, but this is the west coast of North America. It's called the Cascade Range. So shield volcano, cinder volcano, composite volcano. I don't know why they switched to using the word cone on that one. You could say shield cone, cinder cone, and composite cone. It's essentially interchangeable. Questions? Excellent. So we're going to talk about lava for a little bit. Now, remember there were 3 things, and I said we'd work through all of them. I actually kind of thought I had a diagram for the labeling of anatomy of a volcano. I guess it's coming a little later. I would have put it right here, honestly. But. So another pretty picture. We see the lava, the orangish red stuff, right, flowing over this black rock. What do we think that black rock is? Cooled lava, solidified lava, yep. If you just had to guess, you think that looks like rhyolite? Who the hell remembers, right? Black rock is, just told you 2 minutes ago, basalt. Good job. All right, so yeah, this is in Hawaii, more than likely. We do have the quote, the site on here from, this is from an old textbook. Yep, that's the gentleman, and D.A. Swanson there. But as to where the location is what I was getting to. It may have been listed in the text, but even then they just randomly threw in pictures a lot of times. But we're going to assume, okay, we see the black rock and basalt, and we're working on trying to get you guys to remember. So we're going to say that this is a Hawaiian Islands type eruption. One semester, I've been using this slide, as I said, forever. Somebody asked me about those trees because, well, they're encased in that black rock, right? I don't know how they're still standing there. It made for a very photographic moment. That may be partially why they took it and or didn't crop out the trees. I grew up watching Bugs Bunny cartoons, and one of the running gags in that was after someone would get blown up or whatever, they'd go over and touch them or go, and they'd go fall to cinders. For all we know, those things are just about to fall to cinders. But I don't know how they stayed preserved. The lava was cool enough. They're obviously not alive, right? But perhaps by the time the lava moved its way, edged its way over there, they had, it had cooled off enough. Maybe it had just rained. Who the heck knows? But in the background, we see a bit of sputtering and spattering going on again. I know I told you that, the shield-type volcanoes aren't too horribly explosive. That's nothing. Again, that's a mole fountain. Okay. So lava comes in 3 types. You know that. We got your felsics, your intermediates, your mafics. We're going to focus in now a little bit on Cinematic type. How would you guys pronounce that? Pahoho. Okay. Anybody else? All right. Well, that's exactly what I said for about 20 years. And then I was watching a video one day, or maybe even showing it in class. I don't remember. And someone who's definitely more in the know than I am said "boy hoy." I'm like, oh, that certainly sounds a good bit more, pardon the word, Polynesian, right? Pacific Islandy sort of name, word. So it's Pahoehoe, all right? And what Pahoehoe supposedly means is thin and ropey. If you look in the background of this picture, you see those, the surface looks like gnarled tree roots, okay? I think that's what they're referring to. This is a very fluid-like lava. You're going to see in the textbook some words, some conversation using the words viscosity, all right? And in our world, really the only way we know or use viscosity is probably when you're getting the oil changed in your car, all right? If you even use it then. Viscosity is a resistance to flow. So something that's very viscous is something that doesn't flow very easily. In other words, it's very thick. So a viscous liquid is a very thick liquid, all right? This is a lower viscosity. This is a lower viscosity lava. So it's very flowy. This one we're going to say, and I'll have another food reference for the next one in a moment. This one is more like pancake syrup, okay? Just kind of flows out over the side of the volcano. And again, this kind of reinforces what I've been trying to tell you about how the lava just kind of flows down the side. Well, what happens is the air cools off the surface rather quickly. That's why it's really not that red anymore, okay? But underneath, it's still hot. It's still flowing. So what happens then is the surface that's trying to dry gets twisted and contorted, and it looks really kind of cool. It's basalt. This, too, is basalt. The resolution on this picture isn't the bestest, but picture a flaming pile of blacktop, okay? And again, I mentioned I'd use a food wrap. Oatmeal, thick oatmeal. Those guys look concerned?
Yes.
Really?
It's obvious.
The other guy went back to the truck to get some marshmallows, okay? That's how not concerned they are. No, I mean, it's not going anywhere anytime soon. It's a very thick, heavy, viscous sort of flow here. And unless you are that shrubbery or, again, whatever happens to be in the foreground that we can't see here, you've got sufficient time to get out of the way. The thing is this is still basalt, all right? And I know that the 9 rocks we have in lab is enough for you guys. And I know you're tired of me saying, well, this is a 14-week class in and of itself. Hell, you can get a degree in volcanology. So it can be a lifetime. But there are all kinds of basalts out there. Because you got to think that something this thick and chunky, when it cools and crystallizes, even if it's going to be fine grained, is going to look a heck of a lot different than this, okay? So out there in the real world, we don't always see, well, those nice specimens that we have in lab, or more so, they don't necessarily represent everything that's out there. This is called all right? Very, bless you, sort of staccato-y sounding, just, thick and chunky. So, lava. Your book will go on to tell you how this is related to silica content. All right? So even with, and you remember that big arrow that goes across the bottom that Bones reaction series chart and says silica increases to the left as you're going through the mafic to the intermediate to the felsic. Well, even within the mafic, variances in the chemistry can make significantly different appearances in the lava. This is actually a still from a video that I show in, again, it wasn't in the St. Helens video, obviously, but one of the movies I sometimes show. And one of these guys is actually pacing out. He's got a piece of chalk, and he puts a line on the cement or the road there, and then he paces out 10 feet or whatever. He puts another line, and they time it to see how fast the lava's flowing, how long it takes to get to that line, so on and so forth. So, but yeah, they're not. And again, there's another. I show the video right as we're finishing up rocks, and it's a bit of a hodgepodge of things. And again, it's a nice little video break for you guys as well. But there's a handful of volcano things. You're going to see another guy walking over a lava field and grabbing some lava to sample with his rock hammer. All right, so some of these, and anyone been lucky enough to go to Hawaii? Yeah, no, me neither. Take helicopter tours. If you got enough money, they'll drop you down on these things. You know, the insurance companies wouldn't let them do that if it wasn't even, like remotely safe. So there are certainly some areas where you can get to, again, if you have enough money and resources, where you can visit these volcanoes. Some of them you don't want to get anywhere near. So Pahoehoe and Aha, two types of lava that are associated with the Hawaiian Island type eruptions, which again are composite cones, which again is basaltic in nature. All right. Really want to try and make some connections there. There's that dang slide. I'm going to move this slide back to where I thought it was going to be. So next time I give this presentation, it will be there. So anatomy of a volcano. This has a little more than I wanted on it, but it was the most basic one I could find, and it's way better than my chicken scratch. So don't worry about side vent, for starters. Don't worry about ash and lava. But do draw a little upside down ice cream cone in your notes. And then take a bite out of the top, or if you're using a pen, maybe don't draw the pointy bit in the first place. You want to leave room for that hole, the crater in the top, right? Because you'd feel really silly if you lost 3 points on the next test because you couldn't label a volcano because you didn't draw it in lecture class. So the volcano itself, the mountain, again, we call it cone. It's not labeled on here, but we call it a cone. Okay? Yeah, cone shaped. Yep. Not necessarily an ice cream cone. We call a cone because it's shaped like a cone. The word cone came well before ice cream cone, but I figured y'all would know ice cream cone, so that's why we use that reference. Could just as easily be that little pseudo cardboard thing that you put under a snow cone. But yeah, ice cream cone works just great. So the hole in the top is called a crater. And as I said, sometimes it's sealed off. Many times it's snow covered. You look at a lot of these pictures. The St. Helens, they actually did a really good example of that, good job of showing that. A month ago they said, and they showed this snow-capped, beautiful triangular peak up at the top. And then they said, Mount St. Helens today. And it's, this smoking mess. So sometimes they're open and bubbling, not usually. More often than not, they're sealed up. But that crater is attached to a vent, or a vent pipe is what I typically call it. And that's that tube that runs all the way down through the middle and attaches. You see where it starts to get thick down there. The slide doesn't go quite far enough. But a magma chamber, we'll call it. We had the word Pluton, if you remember our igneous intrusions conversation. It's the same idea. Big pool of magma that is the feeder for this volcanic system here. And yes, there could be vents all over the place. I try to keep it simple, and we've got just one center vent in our drawing. And again, a vent pipe. And what you need to do is sort of mentally erase all of this and take it back to day one, where it is just a crack in the ground, and that lava starts coming out and bubbling up and piling up around the vent. Be it the cinder cone sputtery or the shield flowing to the sides, whatever. And yeah, speaking of shield cones, this could happen on the bottom of the ocean as well. Sure, there's tons and tons and tons and tons of water pressure at the bottom of the ocean, but it doesn't match the pressure coming out of the inside of the earth for this stuff. So the lava and the ash are just there to show you this is really sort of, pardon me reusing the word here, but this is sort of a composite structure, okay? It's made up layer after layer of eruptions. And yeah, sometimes there's just some ash that comes out of it. Sometimes there's lots of lava. Sometimes it's just gas and steam. You never really know. So they're just trying to show you that idea. So we really have, I think it's four things. So we have the cone, the mountain itself. We have the crater, which is the hole in the top, where the vent pipe sort of manifests itself. We have the vent pipe, and then we have the magma chamber. So four things, I guess. And I think I remember why this is where it was. Because I then have to move this slide if I want to do it correctly. I'll think about that. So I just mentioned the word crater, and I mentioned the word vent pipe. In the foreground of this picture, there's two things going on here. Don't look at the lake in the back right now. In the foreground of this picture, we have this sort of cone-shaped hole. Hopefully you can see the depth that's implied there. And if you look hard enough, maybe you can even imagine, because it gets kind of black, you can see where that starts to go down into the vent pipe maybe. So that's your crater. It's the top of the volcano. And arguably, if you were 10 miles away looking at this thing, it's going to look like a pointy mountain. You're not going to see the fact that once you get to the top, it actually is, a depression and so on and so forth. So that's what a top of a volcano looks like. In the background, though, I don't want to say more importantly, but equally importantly, we want to introduce the word caldera. And a caldera is not a lake necessarily. A caldera is a collapsed volcano. You see a diagram a little later, another different diagram, that shows, if you've got this last big hurrah of an eruption kind of thing, and the magma chamber empties itself out, huge explosive event that, this thing could just sort of collapse in on itself, blow itself to smithereens, collapse in on itself. We're looking at the rounded nature of this. Now, if that all happens to occur in an area where you get a lot of moisture, a lot of precipitation, snow comes, snow goes, so on and so forth, they do tend to fill up with water. They're giant holes. So quite frequently these calderas are full of water. Not always, but sometimes. So you recognize them again by the almost perfect ring-like structure of them and steep cliffs maybe. So the neat thing about this one, I told you it was a last hurrah, the volcano, the magma chamber empties itself out and blows up and so on and so forth. It's hard to get scale in this image. It's a good bit of a hike, don't get me wrong, but these magma chambers are huge. And the fact that this volcano in the foreground is here, more than likely they share the same magma chamber. The one in the back, way older, for whatever reason, as the magma came back up through that ancient crack that allowed it to fill in the first place, it manifested itself in a slightly different location. All right, and more than likely this volcano in the front here has grown after all that in the back even happened. Not necessarily, this is just an interpretation. Okay, we could obviously go and test the rock, so on and so forth. Maybe they were brother and sister, who knows, and the one in the back just happened to blow up, so on and so forth. But the story I'm weaving, okay, this is what I think. Again, it's hard to get scale, but yeah, mountain size, right? So, ever since I've been here 22 years or so, I every so often find myself slowly spinning around and looking, it depends where I'm at the valley that I'm in, more so looking up at the ridges around me. Because I know it isn't a circle, we're in a river valley, but it can appear circular depending on where you are. And there's this moment, if you're a geology major, you're like summer of your junior year, so just before you go become a senior, or sometimes summer of your senior year, but you go out on what they call field camp. And I've never been to boot camp, and I don't want to be, in any way lessen the effects of boot camp or anything, but we always sort of jokingly called it a boot camp for geologists. They throw you out, as a kid growing up in Ohio, where the most we had, were some mounds of rock that the glaciers left behind, going out in the middle of Colorado and New Mexico and whatever to see actual real geology, man, it was pretty crazy. So you go out there for like a 3-week summer course and get immersed in anything and everything that you can. So one day the teacher said, okay, we're all getting the vans this morning and we're going to go see a caldera. We're like, yeah, hell yeah, let's go see a volcano hole, smoking, who knows, we were picturing the gates of hell or something. I don't know what we were picturing. Not what we ended up seeing. So we're driving and driving and driving, finally pull over to the side of the road, and teachers are just kind of standing there smiling as we're kind of sitting there wondering, okay, where are we going to hike to? I don't see anything anywhere nearby. God, we got another hike. This sucks. What's going on? So they purposely are doing this to us. Finally, he's like, okay, slowly spin around. Okay. So horizon level, way out. There's a ridge of mountains. And we look all the way around horizon, right? All the way around us, okay, was this ring of mountains. We were standing in the center of this caldera. It was probably as big as New Hartford. Okay, it was just monstrous. And it really, again, kind of really changes your understanding of what a mountain, can be, what a volcano can be. It was because you're used to seeing a chain of mountains. You guys live close to the Adirondacks. You got some isolated peaks here and there, but just the scope of this thing was mind-boggling. Nature could make whatever she wants. Certainly had the time to do it. So, but we tend to take pictures again of things that fit a nice, neat view of our camera, kind of things. We didn't have 360-degree GoPros back then and all that cool stuff. So I'm coming to realize it's the conversation about lava that was out of place. I think I'll just move those couple slides instead of all these other ones. I mentioned the Cascade Range a little while ago when we were talking about volcanoes in North America, continental North America. For the geographically challenged out there, like myself, we're looking at the topmost west coast state of Washington. Below that is Oregon, and below that is California. I recently visited California. I had no idea. I mean, I knew it was a long, skinny state, but good gosh, it is a very long state. It goes all the way down to, well, Mexico from there, okay? And again, if you've got a good geography picture in your head, that's a long way. Now you see, we only see a bit of California here because California is much more known for some other geologic event called what? Earthquakes, yeah. All right. But in the very tippy top part, we still see some volcanic activity. And again, it carries through. And then above Washington there, of course, we transition into Canada. We have British Columbia there. All right. And then Alaska's up there. So this does go a bit further up there, but this is generally speaking what we consider the Cascade Range. And it is a chain of active volcanoes in continental North America. If you're staring at this picture while I've been talking, you probably recognized a couple names. Mount Rainier, I mentioned several times. Mount St. Helens is there. You see how that dwarfs in comparison to Rainier. I'm sure this is 100% to scale, right? But I think they did try to, give you a decent idea. Some of these not so commonly heard. Crater Lake, kind of a cool place. That is actually a caldera on top of a mountain. We'll see a picture of Crater Lake in a little bit. These are here for a reason. Just like earthquakes that we tend to see at plate boundaries, we tend to see volcanoes at plate boundaries as well. Again, a plate boundary is where one of the lithospheric plates, the continental plates you might call it, crustal plate, ends and another one begins. It's a seam. All right. And what you may or may not remember from earth science class is that different types of seams manifest as different types of features. We'll get into all that way later in the semester when, if we get a chance to talk more about plate tectonics. But remember, I gave you a little introduction in the very beginning. So this plate boundary is called a subduction zone. Subduct, subdue. All right, subduction zone. And what happens at a subduction zone is that the one plate is pushed underneath another plate. In this case, I want to say in all subduction zones, but I'm not 100% on that one. In this case, the oceanic plate, the Pacific Ocean plate, is being pushed underneath the North American plate, the continental plate. The oceanic plate always loses when you're going ocean to continent. And by loses, I mean it gets pushed down into the earth and remelts. Now this question is going to seem random for a moment, but bear with me. Anybody out there cook for a living? Come on, we've got any SpongeBobs out there? I did that for years. Cooking's a good hobby, but hours kind of stink. Pick a family restaurant if you can. They tend not to be open on holidays as much. So none of you have ever thrown anything into a fryer. You really hurt my story. Well, then how'd you do that if you don't cook?
Chicken nuggets in the microwave.
No, I never did it.
Chicken nuggets in the microwave don't count. No.
I never did it for a living, I promise you.
Okay, how about you guys? You little fry daddy at home on the counter? Yeah?
My brother likes to throw burgers in the grill.
Okay, that's similar, but no, we want to go for the fryer reference here. So, but good for that's a good thing to do. You should learn how to do that. Grilling is a good skill. So, and air fryers don't count either. Air fryers don't. We need a good old vat of oil. All right. So you may or may not know this then, and don't try this at home because it will make a huge mess. When you're cooking and you got to throw something in the fryer, if it is chock full of ice crystals, something kind of evil happens. All right. What is? I see some smiling nods. What happens?
It's just like
Yeah, it bubbles and snap, crackle, pops like crazy. And if there's a nut, and don't ever. That's why they say don't throw water on an oil or a grease fire. All right. It's horrible. It makes more of a mess. That ice. Remember we talked a little bit about phase. Actually, we didn't do water cycling here yet, did we? Yeah. Earth science got it though. So phase changes. You remember phase changes. You go from solid to liquid to gas, so on and so forth. So that ice crystal is going straight from solid to gas, which is a big change. They like to melt first and then evaporate. Oh, it's horrible. It's horrible, and it sputters, and sometimes the whole fryer, if there's enough of it, the whole fryer can start to rise, the level of the oil, it can get scary, all right? So what was the point of that story? Well, this is a plate boundary with an ocean going under continental crust. That ocean plate's going down, it's bringing a whole lot of water with it, whole lot of water. That gets down there and it mixes up with that magma. Way worse than that fryer. That's why we think that we see these volcanoes here. You've got that, not just rock melting back into magma. Extra magma is never a good thing anyhow. But you mix in the volatility of all that water, all right? It puts all that gas in, it builds up, and what we see then is manifesting as these volcanoes. And also notice that those aren't right on the boundary. The boundary's over there at the coast, right? So why are they so far in? Well, that slide, I'm using my hands here. You folks at home can't see my hands. But, this way. All right. Once that goes down, it has to melt. Look where my fingertips are. They're practically at my third set of knuckles here. All right. So by the time that melts and the water bubbles in and everything, you're a good bit inland. So we don't see these volcanoes right on the sea, all right, because, the amount of actual space it takes for this all to happen. Now it's slightly off topic. Well, actually, let me change the slide here because we'll have it here. For those of you that may have heard of the Aleutian Islands, right? Or if you liked in your sociology class or your history class when they talked about the land bridge and all that. Okay, up where that area is. The Aleutian Islands are a volcanic chain as well. And a little south of the land bridge, but nonetheless, it's up in that general area. Up here, the land is pulling apart. Imagine a big cut on your arm or your leg, all right? And it's cracked open and it's bleeding, and that's what the Earth is doing there. So in this case, we see the volcanoes right on the scene. But in the subduction zone, all right, the volcanoes are a little farther off of the scene. And as we said, once you get into California, it's no longer volcanic activity, it's earthquake. Earthquakes, we'll get to those. That's side-by-side sliding. So we actually see the plate boundary style, for lack of a better word, change as we get further south. So that's why you no longer get the volcanic activity. So, at any rate, what you're looking at here, you've probably read the text already. Ring of Fire, you've heard of the Ring of Fire. They even mentioned it in the St. Helens movie. Looks more like a horseshoe here. All right. Goes around the Pacific Ocean. West coast of North America, down the west coast of South America, up across the Aleutians. Now, as you get over to Asia, it is a mess. It is a serious mess. There's a whole lot of what we call microplates over there, much smaller plates, and we try to, continue, and especially as you get down into the islands above Australia and below southern Asia there, it's just a mess. And there's been a lot of large and unfortunate earthquakes and volcanoes in that area of the world. But we carry the whole general idea down. And it does go all the way down to Antarctica. There are volcanoes down there. So the Ring of Fire is also called the Circum-Pacific Belt. Circum as in circumscribe or circumcise. Okay, to cut around is what circumcise means. Circumnavigate. We heard the word circum a handful of times in life. So that's the ring around the Pacific, okay, the belt around the Pacific. And this is the most volcano and earthquakedly active area in the world. Nearly 3/4, in fact, of the world's earthquakes and volcanoes occur here. Now, not every earthquake or volcano happens around the Pacific Ocean. The second most active area is the Circum-Mediterranean belt, all the way over here in the upper left-hand corner. And yeah, I can't spell Mediterranean either, just hack out something. But here's where you see, if you read like Greek and Roman mythology and whatnot, these are all your village obliterating volcanoes of lore, okay? Vesuvius and Pompeii, right? Etna, Thera. So Mediterranean is, you hear that much more for earthquakes, but they certainly have some volcanoes that can go off.
Pompeii's in Italy, right?
Yeah. Kilimanjaro down in Africa there's another thing that's going on. I mentioned the earth cracking open and lava coming out. You may or may not have heard that at some point India was attached to Madagascar, which was attached to Africa. So this comes down, turns around, goes into here, and then actually fits in right up here, kind of underneath the word Kilimanjaro. This bit of Madagascar goes up into there. Africa is slowly ripping itself apart. This bit that comes through the A and the M there is going to separate off. Well, it practically is separated off. I mean, you look at all of Africa, you hardly see any blue, right? Not a whole lot of water there. But you get over here, and it's just riddled with it. All right, it's slowly but surely ripping itself apart. Again, my geography is horrible, so I can't even begin to guess what countries are over here. But at any rate, that area has earthquakes and, of course, very famous Mount Kilimanjaro. Hawaiian Islands. Nowhere near a plate boundary. Right in the middle of the Pacific Ocean. There's another reason for those. And I actually mentioned it a little while ago. I mentioned the hotspot activity. The fact that there's just a pool of lava very close to the surface and the plate is kind of sliding over it, right? And that's what's happening here. Hotspots are also why, I don't know, in my mind it's kind of close to the subduction zone we were just talking about, but the name of the park just jumped out of my head. Yellowstone. Okay? Old Faithful, the geysers, all of that is there because there's a giant puddle of magma underneath there. Okay? That itself is a caldera. That whole park is a caldera, or a couple calderas. A ways back, It's been a while. It may still be making its rounds on Discovery. There was I can hardly call it a documentary because there was an awful lot of sensationalization in it. But Super Volcano, I think, is what they called it. You've seen that one, yeah. Okay. Yes, it is true that Yellowstone could arguably blow up at any given moment. But please don't ever let that stop you from going there. Okay? Honest to God. If you're anywhere near there, go. If it wasn't for the stupid tourists, and we'll ignore the fact that you'd be one, but you'd be a geology tourist now, so that's a little different. You'd think you're on another planet. I had the opportunity to spend a couple hours there one day, and it's truly otherworldly. The bubble pits and the mud pots and the geysers are cool, but it's like being on Venus. It's crazy. But that is another hot spot. Okay, so these hot spots are just these random pools of magma that, for whatever reason, are closer to the surface than magma ought to be. In that case, it heats up the groundwater. All right, and causes some earthquakes here and there. It was rumbling, actually. They closed off a good section of the park a month or so back. And in extreme examples, you see the Hawaiian Islands being made. So, I wasn't talking to you, Siri. So, Circum-Pacific Belt, Circum-Mediterranean Belt. I didn't use the word, but Rift Valley is what's going on with Kilimanjaro there. Rift with an F. Hotspot activity. Lots of vocab on this slide. Questions, comments? Oh, and I did mention Iceland earlier as a volcano. You can see it off of the very tippy top of the right up there. Okay. That is a different thing. There's something that goes right down the center of the Atlantic Ocean called the Mid-Atlantic Ridge. It's the longest, tallest mountain chain on the planet. And occasionally it pokes out of the water. It's there because when two oceanic plates pull apart, when two oceanic plates, pull apart. I told you the wrong thing for the Aleutians. The Aleutians are two oceanic plates coming together. I lied. So when they're pulling apart, you get the Mid-Atlantic Ridge. All this magma comes up from underneath, bubbles up, and builds this huge mountain chain. It's been there forever. At any rate, there's a few places where it pops out. Iceland is one of them. Okay, it is a giant volcano of an island, and some neat stuff there. All right, now questions, comments, concerns, randomness. Okay. Well, I have been talking about stuff for an hour now. So I'm going to quit talking about stuff. And as I still have a couple minutes, even though I'm going to quit talking, I want to show you a video. Really quick, but it is quite cool.